Last time we met the eigenequation. A matrix A times a special vector V gives back just a number lambda times that same V. The vector keeps its direction. Lambda tells you how much it stretches. Now suppose you already know the eigenvalues of A, and someone asks, what are the eigenvalues of a squared, of A inverse, of a plus 5 times the identity? Here is the good news. You never need a brand new characteristic polynomial for each one. The eigenvectors stay exactly the same, and the eigenvalues change in simple, predictable ways. This whole lesson is that short list of rules. Before the transforms, two facts that hold for every square matrix and give you a free sanity check every single time. The eigenvalues, all of them added together, equal the trace, the sum straight down the main diagonal, and all of them multiplied together equal the determinant. Take this matrix from last time. Its eigenvalues were 5 and 2. 5 plus 2 is 7, and the trace 3 plus 4 is also 7. 5 times 2 is 10, and the determinant 12 minus 2 is also 10. The eigenvalues and the matrix agree perfectly. Start with the definition. A hits V, and out comes lambda V. Now hit both sides with a one more time. On the left, that is a squared V. On the right, a meets lambda V. Lambda is just a number, so it slides out front. A times V becomes lambda V again, and we collect a second factor of lambda. So A squared V equals lambda squared V. Keep going, and the pattern is unstoppable. A to the k applied to V is lambda to the k times V. Same eigenvector. The eigenvalue simply gets raised to that power. Here is the picture that makes it obvious. Take an eigenvector, the gold arrow, pinned to its own dashed line, with lambda equal to 1.5. Apply a once, and it stretches along the line by 1.5. Apply A again. That is a squared, and it stretches by lambda squared 2.25. It never leaves the line. Only its length grows by lambda to the power of how many times you apply A. Next, the inverse. Begin, as always, from AV equals lambda V. And this time assume A is invertible. Multiply both sides on the left by A inverse. On the left, A inverse undoes A and cancels it. So the left side is simply V. On the right, lambda comes out front, leaving lambda times A inverse V. Now divide by lambda. A inverse V equals 1 over lambda times V. The eigenvector is unchanged. The eigenvalue flips to its reciprocal. One caveat, and it matters. This only works when lambda is not 0. But a 0 eigenvalue would make the determinant 0. And then A has no inverse at all. So for an invertible A, no eigenvalue is ever 0, and every reciprocal is safe. The last transform is the gentlest. Shift A by adding C times the identity, then apply it to an eigenvector. Split the sum, AV plus CIV. The identity does nothing, so that second piece is just CV. Replace AV with lambda V, and now both terms carry AV. Factor it out. The whole thing is lambda plus C times V. So shifting the matrix shifts every eigenvalue by exactly C, and the eigenvectors never move. Add 3 down the diagonal, and every eigenvalue climbs by 3. It is the single easiest rule to remember, and one of the most useful. Two more shapes worth knowing on sight. First, a matrix and its transpose always share the same eigenvalues. Flip A across its diagonal, and the eigenvalues do not budge. The reason is one clean line. Transposing a matrix never changes its determinant, and a minus lambda I transposed is just a transpose minus lambda I. So both have the identical characteristic equation, identical eigenvalues. Second, the triangular matrix, the real gift. Take this upper triangular T with zeros filling the whole lower corner. Subtract lambda down the diagonal, and a minus lambda I stays triangular. The determinant of a triangular matrix is simply the product of its diagonal. So it factors on site. Set it to 0. And the eigenvalues are handed to you. 2, 5, and 4. The diagonal entries themselves. No polynomial to solve. The same holds for any triangular matrix, upper or lower. Now the most beautiful shape of all, the symmetric matrix equal to its own transpose. When a real matrix is symmetric, two remarkable things are guaranteed. First, every eigenvalue is a real number, never complex, no matter how the matrix is built. Second, the eigenvectors are orthogonal. They meet at right angles. For this S, the eigenvalues are 5 and 3, both real. Their eigenvectors point along 1, 1 and 1, minus 1. The gold and rose arrows. And there it is, a perfect right angle between them. That single fact, real eigenvalues and perpendicular eigenvectors, is the backbone of principal component analysis and a great deal more. Let's put every rule to work on one matrix. Here is and notice, it is upper triangular. We want the eigenvalues of itself, then of a squared, a plus 5i, and A inverse. Step 1. Because A is triangular, the eigenvalues are the diagonal entries. 2 and 3 read straight off. No polynomial needed. Solving a minus 2i and a minus 3i gives the eigenvectors 1, 0 for lambda 2 and 1, 1 for lambda 3. These same two vectors will carry through every transform that follows. Step 2. A squared. By the power rule, the eigenvalue square. 2 squared is 4. 3 squared is 9. And you can verify it directly. A squared times v1 is a times 2 v1, which is 2 times 2 v1, 4 times v1. The eigenvector is untouched. Step 3. A plus 5i. The shift rule just adds 5 to each eigenvalue. To become 7, 3 becomes 8. And step 4. A inverse. First check the determinant. 2 times 3 is 6. Safely non-zero, so the inverse exists. Then the eigenvalues become reciprocals, 1/2 and 1/3. 4 transforms, all from the eigenvalues 2 and 3, no new work. Your turn. Here is a symmetric matrix S. Pause the video and find two things. The eigenvalues of S, and then the eigenvalues of S minus 3i. I'll wait. Here's the walkthrough. The trace is 8, the determinant 15. So the characteristic equation is lambda squared minus 8 lambda plus 15. That factors into lambda minus 5, lambda minus 3. So the eigenvalues of S are 5 and 3, both real as symmetry promised. Now the second part, for S minus 3i, the shift rule subtracts 3 from each eigenvalue. 5 becomes 2 and 3 becomes 0. And that 0 is telling you something. A matrix with a 0 eigenvalue has determinant 0. So S minus 3i is singular, not invertible. If you spotted that, you have truly understood the shift. Beautifully done. Trap 1. The most common by far. For a squared, you square the eigenvalue, lambda squared. You do not square the individual entries of the matrix. Those are completely different numbers. Trap 2. Using the inverse rule on a matrix that has no inverse. If any eigenvalue is 0, the determinant is 0, and A inverse simply doesn't exist. Check invertibility before you take reciprocals. And trap 3. A lovely one to know. If a matrix is idempotent, P squared equals P, then PV equals lambda V forces lambda squared V2 equal lambda V. So lambda squared is lambda, and every eigenvalue must be 0 or 1. Nothing else is allowed. Let's lock the whole toolkit in. A2. The k raises each eigenvalue to the k, same eigenvector. A inverse flips each eigenvalue to its reciprocal whenever the matrix is invertible. Adding C times the identity shifts every eigenvalue by C. A triangular matrix simply hands you its diagonal as the eigenvalues, and a symmetric matrix guarantees real eigenvalues with perpendicular eigenvectors. Through all of it, the eigenvectors stay put, and the eigenvalues follow these simple rules. Learn this short list, and a whole family of matrices opens up from just one.